Finishing up section 6.6 here, we're going to do the got it problem on page 402. It says, you want to build a fence for a rectangular dog run. You want the run to be at least 10 feet wide. The run can be at most 50 feet long. You have 126 feet of fencing. What is a graph showing the possible dimensions of the dog run? So here we have a rectangular dog run. Okay, our length, it says you want the run to be at least 10 feet wide. So our width could be 10 or it could be greater than. 10 is the smallest we want it to be. The run can be at most 50 feet long. So our length can be at most 50 feet. So it could be exactly 50 feet or it could be less than 50 feet. It also says that the total amount of fencing we have is 126 feet, which means the whole way around our perimeter could be less than or equal to 126 feet. So we can come up with a system of equations here. Length, which I'm going to make x, and width, I'll make y. Again, it doesn't matter. X could be less than or equal to 50. Y could be greater than or equal to 10. And my perimeter, in order to find perimeter, it's 2L plus 2W. It's a length and a length and a width and a width. So here I have 2x plus 2y is less than or equal to 126. And this is my system of equations, inequalities. Now, as far as graphing this goes, I made x length and y width. X has to be less than or equal to 50. So I'm going to label these by tens because I'm not sure what else is going to happen. So I want to make sure 50 is on my graph, but also at a point where if we need to see one way or the other, we sure can. And I want that to be a line, and it's an equal to line because it can be equal to in my inequality. Equal to lines are solid lines. So again, you would use your straight edge here to get a line a lot straighter than mine. And I only picked a first quadrant graph here, guys, because we can't have negative lengths. We can't have negative widths. So it's only in the first quadrant. And we want it to be less than. So from that line, I'm going to go this way. For my width, okay, it could be greater than or equal to 10. I also know that eventually I'm going to have to get a pretty big number here. So I'm going to go by tens here as well. And at 10, I have an intercept. I can draw in my line here because it's equal to arrow. And from here, I want it to be greater than, so I'm going to go up. So right now, I want this direction from my blue line and this direction from my yellow line. Now, my third line here, couple options. We can find our intercepts and connect them, or we can use our slope intercept form. I'm going to use intercepts. So my x-intercept, I plug a 0 in for y. And solve. If I plug a 0 in for y, I get 2x less than or equal to 126. Divide by 2. And x is less than or equal to 63. So at 63, I have a point. My y-intercept, I'm going to plug a 0 in for x. And same idea, bring down the rest of it, divide to get y by itself, and again I get 63. So at 63, I'm going to have a point. Now it could be equal to 126 here, so I can go ahead and draw in my line. To connect my two intercepts. And I know those are kind of a guess. I don't have exactly 63 on here, but I feel pretty confident in that. It's close-ish, close enough. And I want it to be less than that. So for this line, I'm going to go this direction. So blue goes in this direction, yellow goes up here, and red goes here. So the area that works for both, or all three, is this part right here. These are all of our options for our dog park. And be careful here in the corner that we don't cross over that blue line. Those are all of our options. A real quick recap here for 6.6. Solutions of a system of inequalities can be graphed in the coordinate plane. And the graph of the solution of a system of linear inequalities is the region where the graphs of the individual inequalities overlap. So it still has to work for all of them, and we see that by graphing and finding where the shading is overlapping, where it works for both. And that's all I have for section 6.6.